Hello everyone and welcome to the next chapter of chemistry, and that is going to be the p block elements. So in the p block elements we are going to strictly discuss with respect to the group number 13 and group number 14. Okay, so as we have already seen about the periodic table, so in this particular periodic table we are going to discuss about the elements which are going to start from the boron to the noble gases. Okay, so when we take a look into these particular elements, what we observe is that in the p block elements, the last electron, or what we call it as the valence electron, okay, so that enters into the valence shell p orbital. Okay, so that means a last electron is entering into the p orbital of the last orbit. Okay, so those particular elements in which the last electron enters into the outermost p orbital, we classify them under the p block elements. Quite simple as that. Okay, so when we take a look into these particular p block elements, as we know about the p orbital, so the p orbitals, there are three p orbitals, that is, we have px, we have py, we have pz. We have already discussed about the shapes of these particular orbitals in the chapter atomic structure. Okay, so px, py, pz. Every single orbital has a capacity to fill up 2 electrons. Right? So 2 electrons will be accommodating in px, 2 electrons will be accommodating in py, 2 electrons will be accommodating in pz. So, can we say that maximum number of electrons in p orbitals? Okay, so it is going to be in p orbitals are going to be 6. 2 plus 2 plus 2. Okay, as p orbital completely, px, py and pz, okay, they together can accommodate 6 electrons. So therefore, what we see is these p block elements are categorized into 6 different groups. Okay, so it has been classified into 6 different groups because it has a tendency to accommodate 6 electrons. It all starts with group number 13, which we call it as the boron family. Further, we have group number 14, which we call it as the carbon family. We have next one, and that is group number 15, nitrogen family. It is also called as the nicogen family. Okay. Next one, we have group number 16, what we call it as an oxygen family. Further, we have 17, group number 17, the halogen family. And finally, we have group number 18, the noble gases. Okay, so because it has a tendency to accommodate 6 electrons in the p orbital, we have 6 different groups for the p block element. And for our studies in this particular PUC first year syllabus, we are going to deal with the boron family and the carbon family only. Okay, this is going to be for our set of discussion. Now let's speak about the general format. Okay, so whenever we take a look into the P block elements, let it be right from the group number 13 to 18. Okay, what we see is the first general thing, that is the general electronic configuration. Okay, so general electronic configuration for the P block element is going to be as ns2. That means s orbital is completely filled, np1 to 6. That means we are going to go on filling the p orbitals. Okay, quite simple. If only one electron is entering into p orbital, we classify them under the boron family. If two electrons are coming under p orbital, we take it under the carbon family. If 3 electrons are coming into the p orbital, nitrogen. 4 electrons, oxygen family. Okay, so on and so forth. So we can say that by the time that we reach the noble gases, all these p orbitals are completely filled. Okay, because it is completely filling the p orbital, these set are not so reactive in their nature. This is how we have to think. Okay, so the general electronic configuration is ns2 np1 to 6. Right. So coming forward with the next point of discussion, and that is going to be the oxidation state. Okay. One thing that we have to understand is, because of its big, huge group now, these particular elements have a tendency to show variable oxidation state. Okay, and the oxidation state is equal to the number of electrons these particular element have in their valence shell. Okay, so oxidation state is equal to the number of electrons in their valence shell. Okay, let us take one particular example in order to explain this statement of mine. So let's take here atom nitrogen. Atomic number of nitrogen is 7, right? So electronic configuration will become over here as 1s2, 2s2, 2p3. This is what is going to happen. So valence shell are nothing more than these, because it's an outermost one. Okay, so here oxidation state for nitrogen is +5. It varies from +5 to -3. Okay, now how is it +5? Is because number of electrons in s orbital plus p orbital, okay, of valence shell. So if we take that into consideration, 2 plus 3 is 5. So oxidation state for the nitrogen is going to be +5. Okay, so that is going to be equal to your oxidation state. Quite simple as that. Okay, so taking this thing into consideration, we can have the oxidation state for the groups, which we are going to discuss now. Okay, as we take a look into the P block elements, this particular P block element is been categorized into 6 different groups, right? The group starts with group number 13. So let's write over here. The groups that already have is starts with group number 13, 14, 15, 16, 17, and finally 18. Right. Now, let's observe what is going to be the first element of all of these particular groups. So, starting with group number 13, what we have is the boron family, followed by we have carbon, nitrogen, oxygen, halogens. Halogen starts with fluorine, and over here it starts with helium actually. Helium will be on the top. Okay, now as we observe the group oxidation state. Okay, as we observe the group oxidation state. So, in order to understand the group oxidation state, first thing what we require here is the electronic configuration, general electronic configuration for that particular group. Okay, so taking that into consideration, we can write it down as the general electronic configuration. So, general electronic configuration for boron is going to be as Ns2 Np1 for this entire family. Okay, followed by for group number 14, it is going to be as Ns2 Np2, followed by Ns2 Np3. For oxygen, Ns2 Np4, fluorine, that is a halogen family, Ns2 Np5. Finally, coming over here, we have Ns2 Np6, completely filled. Correct? Now, here when we observe the group oxidation state, so, for the oxidation state, what we had seen is the total number of the electron which are present in s orbital plus the total number of electron which are present in the p orbital. The sum of these together will give us the oxidation state, right? So, taking that into consideration, when we get here, that is 2 plus 1, we have plus 3. Okay, now here for 14, we have 2 plus 2 plus 4, 15, 2 plus 3 plus 5, 2 plus 4 plus 6, 2 plus 5 plus 7, finally 2 plus 6, what we have is plus 8, right? So, what conclusion can we draw here is, as we move towards the left, towards the right of the periodic table, right? So, the oxidation state what will happen is keeps on increasing. So, therefore, as we move towards the right of the periodic table, the oxidation state increases, and that is what we have put here. Right. So, now moving forward with the next one, and that is when we observe certain elements in this particular case. The oxidation state is somewhat, let's say, +6 according to the group oxidation state. But some element of that particular group tends to show an oxidation state less by 2 units. Okay, so therefore, some elements in the group tend to show the electronic configuration less by 2 units than the group oxidation state. Now, this happens. Usually this happens because of one finest reason. And the reason you require to remember, and that is, it is all due to, this is entirely due to one concept, and that is due to the inert pair effect. Because of the inert pair effect, the electrons which are present inside the core, which are completely filled, which we cannot give the electrons. Okay, because of that, this particular oxidation state is being observed. Okay, so second point that what we have to concentrate in the p block elements is that there are certain heavier elements. These heavier elements, especially from the third group onwards, okay, so from the third group onwards, whatever these heavier elements are there, these heavier elements involve the presence of d orbital electrons. Okay, so we have to remember this important point. So the elements which starts over from the third group and next ones, these particular heavy elements will involve the presence of the d orbital electrons. Okay, so let's observe the next concept. When we observe these particular p block elements, when we observe these particular p block elements, that is from the group number 13 to group number 18, we observe the presence of even the non-metals, as well as there are the presence of metalloids. Okay, so there are non-metal as well as there are the metalloids. Now, when we observe about the non-metals, these non-metallic characters are perfect with respect to the lighter elements. Now, lighter elements in a sense, the particular first element of that particular group. Okay, so these non-metallic character, as we go down the particular group, Okay, as we go down this particular group, these non-metallic character goes on decreasing. Okay, as it goes on decreasing, the elements which comes down successively will be having more metallic type of characters. Okay, so that means we have another one that is going to be over here, the metals. So P block elements contains about metals, non-metals and metalloids. Okay, so therefore when we observe about these, that is non-metals or non-metallic elements, what do we find in this particular case is that the first and foremost character of non-metallic elements is that they have very high ionization enthalpy. So first thing that what we observe, what we notice is about having an high ionization enthalpy. Second point is what we observe in these non-metallic elements is that because of the high ionization enthalpy, they also exhibit high electronegativity. In contrast to those of the metallic elements. So, in the case of metallic elements, what happens is these particular elements will exhibit low ionization enthalpy. Now, any particular substance which is called as a metal, it has a very good tendency to donate electrons. As it has a very good tendency to donate electrons, it is highly electropositive in nature. Okay, because of these, the non-metallic element have a very good tendency to form an ions. That means the elements which are existing at the top of those particular groups have a tendency to become anions. They have a tendency to accept the electron and get converted into negatively charged species, what we call them as anions. While the elements which are coming just below them, as the metallic character goes on increasing. Okay, so therefore, as it forms a metallic in nature, it shows a low ionization enthalpy and higher electropositive nature, due to which these have a tendency to form positively charged species, what we call them as cations. Quite simple as that. Okay, so therefore, these are the two facts about the P block elements, what you have to remember. Okay, so moving further, how to distinguish between the non-metallic and metallic elements? Now, the metallic and non-metallic characters are best illustrated by the formation of metal oxides or metal hydroxides. Okay, so whenever those particular elements will be forming metal oxides or metal hydroxides, if it is formed from a non-metallic character or non-metallic element, if non-metallic element forms a metal hydroxide or metal oxide, then it will be either acidic in nature or neutral in nature. While if this particular metal oxide or metal hydroxide is formed from a metallic element, okay, as it forms from a metallic element, what we observe is that the character is going to be basic in nature. So, it is best illustrated by taking into consideration of metal oxides or metal hydroxides. Okay, so this was as how do we predict about the metallic and non-metallic characters using an oxide and hydroxides. Okay, so let's observe the next one. When we observe the p block elements, what we do see is that there is a distinct character differences between the elements which are light. Now, what I mean by the lighter element is that nothing more than the elements which are present at the first section of the group, okay, such as the boron, carbon, nitrogen, oxygen, okay, so on and so forth. So therefore, when we take a look into the lighter elements, these particular lighter elements show the properties which are not similar to those particular properties of the heavier elements. Now, why does this particular thing happens? It is because when we observe the lighter element, the first thing that we notice is the presence of smaller size. Due to the presence of smaller size, it has direct effect on its ionization enthalpy, it has direct effect on its electronegativity. Okay, so therefore, due to the smaller size, these particular elements are going to show the properties which are not similar to that of the heavier elements. While the second property, the main property, why these particular heavier elements differ from the elements on the top is because in the heavier elements, there are presence of d orbital electrons. These d orbital electrons are being used as valence electron. So whenever these things are used as valence electron, okay, it has direct effect on the nature of bonding here. That is, due to this, the bond that is formed is the pi bonds. Okay, so the pi bonds are nothing more than presence of multiple bonds. So we can say that the heavier elements have a tendency to form multiple bonds also. Okay, multiple bonds, that is the double bond and triple bond in this particular case. Okay, so therefore it is all because of the orbital electrons. So these are important characters. Right? So now we'll start our studies with respect to the first one, and that is with respect to the group 13, what we call it as the boron family. We call it as a boron family because the first element of this particular group is boron. Okay, so in boron family, the elements that we are going to encounter, the elements that we are going to see are, it starts with boron, followed by aluminium, followed by gallium, followed by indium, thallium, and finally what we have is UUT, unantrium. Okay, so unantrium, thallium, indium, gallium, aluminium, and boron. So these are the elements. Okay, so here when we observe, in this particular case, we can apply the same concept as what we had before. The concepts that we had studied at the beginning of the session. That is, as we come down this particular group, metallic character goes on increasing, non-metallic character decreases. Okay, that means over here, when we observe boron, okay, so boron is a non-metal, while the ones which are below here, right, from aluminium, gallium, indium, thallium, and unantrium, all of these are metallic in nature. They are metallic in nature. When we observe about unantrium here, what is one more thing that we observe is that unantrium is not just metallic, rather it is also radioactive in nature. It is recently discovered element. Okay, and it is radioactive in its nature. Okay, so let's observe the next concept here. So, when we observe about boron, this particular boron is non-metal because of, first point is because of the smaller size. Okay, second one is because of exceptionally high ionization enthalpy, and third one is because of its high electronegativity. Because of these particular reasons, what we can say is boron exhibits a non-metallic character. Okay, now aluminium, over here on the other hand, aluminium, though it is metallic in nature, it still exhibits properties which are similar to boron. Okay, so this is one of the things what you require to remember. Okay, let's go for the next one. Take a look into the element boron. Now, when we are speaking about boron, the first thing that we have to remember is that boron is one of the most rarest elements. Okay, so it is so rare that it forms just 0.0001% of mass of Earth. Okay, so it just forms just 0.0001%. Okay, mass of Earth. Secondly, this boron exists in two isotopic forms. So therefore, it exists in two isotopic forms. So the two isotopic forms of boron are B10 and B11. B10 form is available in 19%, while B11 is obtained almost up to 81%. Okay, now let's observe about the chief minerals. Let's observe about the chief minerals of this particular boron. So first one, as we have, is borax, also called as tin can. Okay, so borax or tin can has formula Na2B4O7.10H2O. While the next one, what we have is carnite. Carnite has almost the same composition. The difference is with respect to the water of crystallization. So the water of crystallization, that is 10H2O in this particular case, here it is as Na2B4O7.4H2O. This is the major difference between the two. Okay, third one, colemanite. So colemanite is Ca2B3O4OH thrice 2 times 2H2O. So this is colemanite. Okay. Fourth one. So fourth one is orthoboric acid, which we usually give it as H3BO3. So these are the chief minerals of boron. Let's observe the next one. So speaking about the next element, and that is going to be it is aluminium. So aluminium is the most abundant element. It is the most abundant element. Rather, we can say that it is the third most abundant in nature. Okay, standing after silicon and oxygen, the third one is aluminium. It is obtained, or you can say that it is almost 8.31% when we compare to that of mass of Earth. Okay, so it's all about the element aluminium. Let's observe about its important minerals. So chief minerals. So first one is the bauxite. Okay, so Al2O3.2H2O. Simple aluminium oxide dihydrate. Okay. The next one, corundum. It is an oxide, Al2O3, same one, correct. Cryolite. So, cryolite, Na3Al F6, cryolite. Final one, that is mica. So, mica, K2O dot 3Al2O3 dot 6SiO2 2H2. These are quite very important minerals with respect to aluminium and boron. I would suggest that you write it down, keep it ready. These are important for our competitive points of view also. Okay, so we'll meet you in the next video. Till then, do take care.